All right, so what we do today is combine this weird multilinear algebra we've been doing with calculus. So calculus returns
Sorry.
So we've got these weird dx sub I things that are basically encoding k-dimensional signed volumes if you have vectors in Rn. Now we want to be able to put functions as coefficients and not just constants. So recall that we've got lambda k of Rn star is the vector space of alternating multilinear functions that eat k vectors in Rn. This is a vector space with dimension n choose k, and the basis vectors are the dx of i's where I is an increasing multi-index of length k. All right, so far this week, all we've been allowed to do is take linear combinations of these guys with constant coefficients. And now what I want to do is say, well, let's allow ourselves to put functions as coefficients. Let's now allow smooth functions and for pretty much the rest of the course, unless I specify otherwise, I actually want to just deal with smooth functions, meaning C infinity. I don't want to worry about weird issues with C1 but not C2. I just want to assume smooth.
So the linear maps in lambda krn star, however you refer to them, they're from Rnk to R, right?
They're from k copies of Rn.
So R to the n times k. So R.
Yeah, I'm not thinking of it that way. I think of it as Rn cross itself k times, even though it's officially what you said. You want to think of it as k vectors from Rn. All right, so now I want to allow smooth functions as coefficients. So for example, instead of just allowing myself to write 2 dx1 wedge dx2, I'm now going to allow myself to write e to the x y dx wedge dy. And take sums of such things with different functions. But remember, the point is you always have to, when you're doing sums of these things, you always have to have a fixed k. You aren't allowed to add somebody in lambda 1 to somebody in lambda 3. To have a vector space, you have to have a fixed k. However, what did we learn yesterday? We learned that you could multiply with wedge and take k and l and get k plus l.
But the n has to be the same.
The n has to be the same. So the notation I'm going to use is for any open set, for now anyway, u in Rn, denote by script a k. So the script a is supposed to remind you that it sort of looks like a lambda. No? You don't like that?
No.
So it's still going to be alternating, but now still eating k vectors, but now coefficients are going to be smooth functions. So denote by AKU the vector space of all expressions of the form summation fi of x. So these are going to be scalar functions that multiply the dx's. Where these are now fi are smooth functions on u. And such things, such objects are called, and some people call them differential K-forms on U. So here's the dreaded word differential forms that we're keeping track of the K here. So a one form means that you have a 1 here, which means it's built out of dx's with only one subscript. A 2 form is built out of dx's with 2 subscripts, or you can think of that in terms of dx of I wedged dx of j, for little I and little j. So basically, the K says how many dx's are wedged together to make that dx sub multi-index. We're mostly going to drop this notation and write things with wedges from this point on. Okay, so what algebra can you do with differential forms? Well, all the same stuff that we were doing the last 2 days with constant scalars here, all the same algebra works. So you still have addition, you still have scalar multiplication. Now, in fact, you can multiply by functions. So those of you who go further in algebra will discover that there's a name for, this is really more than a vector space, because you can multiply not just by real scalars, but in fact by functions. So it's like doing linear algebra, where instead of your coefficients being scalars, they're allowed to be functions. And there's a name for such a thing.
Non-linear.
Well, no, it's called a module over the ring of smooth functions. So,
Is it quadratic forms?
no, that's a different. Again, in math, there is overuse of certain words or very closely related
Just
words.
normal. The UV principle.
So we can add, we can multiply by functions, but what else can we do? We can wedge. So we can multiply, we have wedge, which allows us to take K forms together with L forms and end up with K plus L forms. And what properties did we state about that yesterday? We said wedge product was distributive, skew commutative, and associative. So all that's still true. Because all that was just purely algebra. It had nothing to do with the coefficients in front. So still distributive, associative, and then the funny minus sign that shows up when you try to commute. All right, so what's going to be new in the story, as I told you guys yesterday,
Why is there so
Wait, what's that?
Why is there so much?
It's a great letter.
well, because I want to be able to take
Of course it is.
so many dx's with so many dy's with so many dz's,
Oh.
right? So you have to take linear combinations of the basis guys. So calculus comes back. So there's going to be a way to do derivatives.
It's in Kirby B.
New.
Did you decide to write what's new in the story just so you could use that?
It just came to my mind.
Right.
It's true. All right, so there's going to be this creature D, which is going to be a derivative that's going to map K forms to K plus 1 forms. Now, a pedantic person in the audience, but luckily we haven't any, might want me to put a subscript and say this is d sub k. For each k, there's going to be a way that sends k forms to k plus 1 forms. But I'm not going to write different symbols for the d. So you'll understand from context, this time it's eating a 1 form and spitting out a 2 form, or this one's eating a 4 form and spitting out a 5 form. I'm not going to make a different symbol. So here's what d does. First of all, when you take a function, it's going to, so functions are 0 forms, right? Remember we said yesterday scalars were what happened when you did lambda 0. So A0 A0 denotes functions. What should df be? Well, it should be a 1 form.
Is D a function?
Mm-hmm. It's a function on functions that give, it's a function on forms that gives you other forms. It's really an operator. It's transforming things in this vector space to things in this vector space. All right, the rule for df is that you take the partials with respect to your variables and use those as coefficients of the corresponding dx's. Now, those of you who have looked at chemistry books or physics books or econ books have seen formulas like this without anyone making any effort to be so fancy with what forms are. Some people talk in calculus about differentials. How many of you had that in calculus where they said dy was something dx?
Mm-hmm.
So there's a classical engineering abuse of notation where people think about, okay, if I have a function of variables x1 to xn, and I change the variables a little bit, then the function changes approximately this amount. And they call that the total differential of the function. We're trying to be a bit more formal, but it's all going to come out to be the same formally in the end. So what does this remind you of?
The dot product or the gradient vector?
This reminds you of the gradient vector, or of the entries of what?
The derivative vector.
No, no,
Derivative matrix.
The derivative matrix. Hessian is second. So now remember now, what is a 1 form? So a 1 form needs to be something that depends on where you are, and then it's got differential form, it's got the dx's sitting there. So if I take the derivative of f at some point, let's say a, df at a should be built out of the partial derivatives at a. So those are now numbers multiplying the corresponding basis guys dx1 up to dxn. But what does this remind you of? It reminds you of the derivative matrix.
Multiplied by a.
No, not multiplied by a. The derivative matrix at a is the matrix of partials at a.
Right, so level d f of a is just the derivative matrix multiplied by a.
No, there's no, you're misspeaking here. The derivative matrix only makes sense if you are at a point. We normally suppress the notation. We have been a lot, but last semester I didn't. df at a is the linear map that gives the best linear approximation of f at a. And what does that do? It wants to, this linear map wants to eat a vector v. And what does this represent conceptually?
Directional.
Louder?
Directional derivative.
Directional derivative. Right? That was our theorem that if you had a differentiable function, then you could compute directional derivatives by using the derivative of the linear map. So you have to have this linear map that eats a vector, and then you get the directional derivative in the direction of the vector. Well, that's exactly what happens here. The one form, once I put in A, then it wants to be one of these things that's just a scalar. Once I put in A, I have a scalar here times dx. That means that's in lambda 1 of Rn star, so it wants to eat a single vector. Well, so df at A wants to eat a vector v, and what's it going to do? Well, it's going to take df dxi at A times dxi on the vector v summed on I. Now recall, what is dx sub I on v? The ith coordinate of v. So this is just multiplying this matrix by the vector v.
Which is what I was trying to say.
So this is just dv of f at A again, the directional derivative. So the one form df is just giving you back the derivative as a linear map at every point.
What equals from k is okay?
Well, here I started in A0, and this is in A1. I started with a 0 form, and now I've got a 1 form. So I've gone from 0 to 1 so far. Now I'm going to tell you how to do it in general, then we're going to do a bunch of examples. So in general, if omega is a k form, then I can represent omega as a sum of functions times dx's, where the dx's have k components to them. It's a multi dx with k subscripts here. And the rule is, I'm now going to define a k plus 1 form by taking the following formula. Very simple. Take these coefficient functions. Take d of them. This is now at x. df sub I is a what? F was a function. df is a one form. What can I do with a one form if I already have these k things sitting here? I can wedge them.
So it's kind of inductive.
Recursive, if you like, yeah. Well, except it's really, all you need to do is do functions, and then you can just plug that into everything. You can still think of it as recursive if you want. Okay, that's the rule.
So dx sub I is a k form, and you're wedging it with the
A one form, so you get a k plus 1.
Okay.
So let's do some, before I start listing properties, let's do some examples of this. So it won't take you long to get good at this, but let's just do a simple example. Let's do some examples. Let's say f is the function e to the x sine yz. I don't want to write out 6 million terms. What's df going to be?
E to the x sine yz, then dx.
So here's a function we're supposed to take its 3 partials with respect to x, y, and z. And you put the partials you bookkeep, instead of putting them in a matrix, you bookkeep by putting coefficient with dx, coefficient with dy, coefficient with dz. It's the exact same calculations you've been doing. So there's the x partial. So it goes with dx. What's the y partial?
Z
Y
dx cosine yz.
That goes with
dy.
y. And what's the z partial?
Y e to the x cosine
Okay.
dz.
So it's first example. Let's do, suppose I take omega now to be a 1 form on R3. So I'm going to write omega, I'm just going to make up one at random, more or less. Suppose I took y dx plus z dy plus x dz. These are functions, right? That are each coefficients of the basis 1 forms. How do I take d of it? Take the coefficient function here, which is y, and I take d of it. Well, officially, how do you take d of y?
You do the partial of it with respect to x, which is 0.
For
Then you
y,
get
they just,
1 times dy.
So if you follow this rule for taking d of a function, what does it give you back? It gives you back just dy, which is what you would have thought it was. I mean, officially you would say, take partial respect to x times dx, plus partial respect to y times dy, plus partial respect to z times dz. So you end up with 1 dy. And what do you get here? dz wedge dy, and then dx wedge dz, and those are all the 3 different basis 1 forms. You can't combine those in any way. Well, that was sort of boring.
Why do you get the y dx? The first one? Can you explain that?
I did explain it twice. What don't you understand?
I got lost.
How does that follow from our definition of the exterior derivative?
Because the rule was take d of the function,
And
wedge
that.
with dx. Take the function, you take d of it, wedge with what you had.
But wouldn't you also be wedging dy with dy as well? Like, wouldn't there be a...
We talked this through 3 times. We said dy means officially partial with respect to x dx plus partial with respect to y dy
Right.
plus partial with respect to z dz. And you guys told me that those were zeros by definition of partial derivative, and that was a 1. So in other words, dy is dy.
Okay.
Why is there any wedging with one?
Because I had a function, so I'm back in this case. Now I've got 1 form, so I have to take the coefficient functions, d them, and wedge with the dx's that they were sitting next to. I don't know.
Why do you only wedge them with the dx's they were, with the d's they were sitting next
Because
to?
that's what the rule is. You start with an expression,
Oh, okay, okay.
and you differentiate the coefficient function and wedge with the thing it was the coefficient of.
All right, thanks.
All right, let me do a little more complicated one here. Suppose I took omega to be x plus y squared dx plus yz plus x dy plus z cubed plus 3xy dz. Now what's d of that?
Okay.
All right, Jonathan, I'm going to make you do it.
dx plus
Wait,
2y
wait.
plus
I said I'm making Jonathan do it.
Well, first.
So,
derivative
what's
respect
the
to x.
derivative of this?
Well, it doesn't matter because it's going to go up to dx of dx, right?
Yeah.
All right, well, just tell me, what's the derivative of this?
1.
No. What's the derivative? D of this. What's the partial respect to x?
dx.
No, the partial respect to x is 1.
Yeah, so
That becomes the coefficient of dx. What's the partial respect to y?
2y dx.
That becomes the coefficient of dy. What's the coefficient partial respect to z? 0. So 0 dz. Now I put wedge dx. All right, keep going. What's d of this term?
1 dx. Z dz.
All wedged with dy. Now what's the partial respect to, what's the d of this term?
3y.
3y dx. 3x dy. 3z squared dz.
dz.
Wedged with dz.
All wedged dz. Now, let's simplify. So, I think Jonathan was observing something which we're now going to say. What happens to this term here?
It's going to go away.
It goes away because
dx wedged with dx is 0.
dx wedged dx is 0.
And
Because
then
that's
because
dx sub
there are
1,
three-
1 officially, right? You have repeated index. So what am I left with? I'm left with 2y dy wedged dx plus
dx wedge dy
plus.
whatever the
y dz wedge dy.
So again, the dy term disappears. Plus
3y dx wedge
3y dx wedge dz plus 3x dy wedge dz, and then again the dz wedge dz goes away. And we probably could combine some of these. This is the answer, but we could simplify. How many dx wedge dy's do we have?
1 minus 2y.
1 minus 2y dx wedge dy. Why the minus? We switch the order here. When you switch the order, you get a minus sign. That's the skew commutativity. So we've got these two terms. How many dy wedge dz's?
3x minus
And then what's left?
3y dx wedge dz
3y.
That's what it is.
So we're getting sets of 2's because when k equals 3,
So again?
these are all sets of 2's. Is that because when k equals 3, or is it always sets of 2's?
Sets of twos. What do
You
you
mean
mean?
like 2 things wedged?
Yeah, 2 things wedged.
Well, that's because we started in 1 and then went to 2. Right? D omega is in A2. So that's why there's 2 things wedged.
So that's why when k r and star given in it's
0.
because
You don't have enough dx's.
it won't have to be doubled.
Yep. Yep. So, suppose I started with, say, phi in A2 of R3. Say it's given by x e to the z dy wedge dz plus y cosine x dz wedge dx plus x cubed plus y cubed plus z cubed dx wedge dy. What would I get if I took d of that? Well, this is now in lambda 2. So if I take d of it, I'm going to, or a2. So if I take d of it, I'm going to be in a3. And what's a base? Yes,
Do we have to have all the different permutations of
you do not.
dx, y, z?
well, not all, but I happen to write down one for each of the three basis guys. But sometimes you could have zeros. So what's d phi going to be? So what's d of this?
So
Well, it has an x partial and it has a z partial. The z partial I don't care about because there's a dz here. So rather than write it all out, I'm just going to now start shortcutting and say, I'm going to take the partial respect to x, dx, wedge with what's there. Now officially, there are parentheses there, right? Because I'm wedging with what was there. But we've already said it's all associative. I don't need to put parentheses in. What about here?
So cosine of x, when dy, when
Yeah.
dz, which dx. And then re z squared dz, which dx, which dy.
Now, for future purposes, it's convenient to collect terms. And what's the basis 3 form on R3? It's dx, which dy, which dz. So you have to think to yourself,
That should be a wedge.
how many switches do I have to make to get them all in that order?
That should be a wedge.
So
Whoops.
e to
Thank
the
you.
z, e
You
to the
make
z
2 in the middle
plus
one,
cosine of x.
and 2 in the second one. So they'll all be,
They're all going to be positive.
So this will become more important as we go on in the chapter, but what made it come out that you didn't have to take care of any minuses is that I sneaked it in on you without saying anything. What did I do now that you look at it that's surprising in hindsight?
The dz dx.
Right, I put this one not in increasing order.
Oh, it's like a loop.
I put this one not in the order you expected exactly so that when I took the y partial I would have dy, which dz, which dx, which would be the same sign as dx, which dy, which dz. The hint is this is related to the minus sign that appears with cofactors,
Or the
or definition of cross product
Yeah.
determinants. It's all this. So the fact that I put dz, which dx there, you could have a problem where it says dx, which dz, you just do it, but I'm getting you ready for what happens when we get to doing surface integrals soon.
sorry, good.
Now here's a question for you guys. What would happen, this one's a little messy, but what would happen if I took d of something I'd already taken d of?
So like DD of
What is d of the df we already did? So go back to number 1 and take this one form and take d of it. So,
it's
so by the way, let's notice, because we had e to the x, as you always noticed in calculus, there's going to be an e to the x in everything. So rather than write it down every time, I'm going to just factor it out.
Would it expand just if
It's
we
gonna
kept
be
taking
zero.
the differential? Would just keep expanding.
So
Well, I got to take the partial, to take d of this term, which partials of this matter?
Well, these y
Y and z. So I'm going to have e to the x cosine yz times how many dy's?
Oh, well, you're gonna get,
I'm taking partial respect to y, I get a z out in
Z
front,
plus W. So Z plus 1.
and then I get a y in front of the dz,
What's the W?
and then that's all wedged with dx. Agreed? Now I have to take the d of this piece. Well, which partials are going to matter now?
x and z.
X and z. So I'm going to get the x partial is going to be e to the x, still sitting there, z
Cosine
cosine yz dx And what's the z partial going to be?
Wait, how did the z come out of there?
Product rule.
Because I'm
Oh, wait, yeah.
I'm doing the partial with respect to x, I just get the coefficient of e to the x.
Yeah.
Now I'm doing the partial with respect to z. Oh gosh, it's going to be two terms, isn't it?
Yeah.
We get an e to the x cosine yz plus
e to the x. We have
z
Z.
times the derivative of cosine yz with respect to z, right? So I'm going to get a y sine yz. All of that dz. Agreed? I should have done an easier example, but you guys ought to be able to do all this. That's all wedged with dy that was sitting there. And then the last term is so much fun. I have to do the x and the y partials of this one. So the x partial is easy. The e to the x is sitting there, and I just have
Y
y
cosine YZ.
cosine yz dx. What's the y partial?
EZ.
Same mess we just went through,
Yeah.
analogously. So we're going to have a
E.
cosine yz plus y times negative sine
Sine.
yz multiplied by z by the chain rule. So that's all dy, and then that whole thing is wedged with dz. And then there's a closed bracket because I had to eat the x outside. All right, what a mess. Yeah.
Why is it, for the first term, should it, why is it cosine of yz? Not like sine of yz?
Because I'm doing the partial with respect to, oh, what happened?
No, that's right.
We were differentiating with respect to y with respect to z.
Right. Oh, right, okay, yeah, you're right.
Okay.
Also, didn't you mean to write sine on that very last cosine?
Gosh,
Yeah.
I did. Thank you. This is why it's easier for you sitting there to see everything I can't see over there. All right. Well, what happens?
It all falls apart.
It all falls apart. Let's look at the dx wedge dy stuff. And I'm not going to go through and check all of it, but let's look at the dx wedge dy. So I've got a dy wedge dx here. I've got a dx wedge dy here. And I've got a nothing here, because those all have dz's. So what happened with the dx dy? Well, I've got the e to the x out front, and then I've got minus z cosine yz. Why minus?
Because you flipped the
Because I
x.
switched the order. What have I got in this term?
Can't see where it is.
Z cosine yz. Looks like 0. And you can check the dy wedge dz and the dx wedge dz, they can all be 0. If I took this omega, we took d of it. If I take d of this, what do I get? Well, this is, what's the coefficient function in front of the wedge of dx's?
1.
What's the derivative of 1?
0.
So what's d of this?
All 0.
Well,
So d of d omega is 0.
what's d of this?
I'm assuming 0.
Well, let's check.
Does it depend on what, like, what K is?
Mm-mm. Well, here I've got a 2 form. If I take d of it, I should get a 3 form. What's d of this?
The first one is 0. You're just gonna get a
Nothing here. What do I get from this term? 3 dx wedge dy wedge dz. What do I get from this term?
3
3 dy wedge dx wedge dz,
Which would be
which
minus.
is negative of the first one, so you're going to get 0 again. Anybody want to hazard a conjecture?
D of D omega is 0.
Hmm?
It's only 0 for these specific examples.
Right.
You're cherry picking these, aren't you?
It's a good thing you're a stat major.
Does that matter?
So this screen should be major.
So
Actuarial science.
to most of the real world, we've done a proof. So what have we got for properties of D? Well, certainly it's the case that if I took D of a sum, so if omega and phi are both k-forms, and I took D of their sum, what do you think I'm going to get?
The sum of the D's?
Sum of the D's, because that's how we defined it, was in terms of sums of things. We just said it was the sum of the D's. So this is automatic. Now, more interesting is, and so the thing that we've just observed now is that if you take D of omega and take D again, we're conjecturing you always get 0. Those of you who have seen multivariable before should be thinking this actually might seem familiar from something.
But it should be a k plus 2 form?
This will, yes, if you take D of omega, it's k plus 1, then you take D again, it's a k plus 2 form. Now here comes the fun stuff. If omega is a k form, and phi is an L form, well, what do you think D of omega wedge phi should be? So I'm asking for a what kind of rule here? What does this remind you of from calculus? What are you doing with omega and phi? You're doing what?
It's like a tree.
Multiplying.
No. Product rule. This is like a product rule. You're multiplying two functions, how do you take the derivative? Well, we're multiplying two forms, how do we take the derivative? Anybody want to guess? Chris, you're cheating, because you've been here before.
Plus
Ooh, be
omega
careful.
Plus omega wedge d phi.
All right, so that, remember, anytime you switch orders, when you were doing functions, you got away with it. But be very careful switching orders of things. You better not mess with the order here. You better keep it omega and put a d phi here. But the problem is, it's still not right.
You need negative?
You need a plus or minus. So there's a -1 to the k. Omega is a k form, and so you can imagine having to move the d across those k thingies to get it to the phi. And that's, I'll show you on Friday.
Now why
You're
did
gonna
you
get a
not
nice
do
one.
that for the first,
Because it was already in front.
Okay.
It's sitting right there. So I'll show you on Friday a proof of this. It's not that hard.
It'd be like, I'm talking about for the fee. Why'd you not have to do like a -1 to the L?
I didn't do anything with the phi.
I know, why not?
It's just sitting there. It's only when I want to differentiate that I have to pay attention.
And yeah, but you weren't doing anything to the omega in the second term.
But I had to move the d across the omega to get it to the phi.
Okay.
And to do that, you'll see in the proof that you're going to get the minus sign. Now, a special case, if you took a function, what's d of a function times omega? So f is a 0 form. What happens with this formula then? You get df wedge omega plus -1 to the 0. So you're just going to get f times d omega. So the special case here when f is a function. Okay. So this is literally a product rule. This is something we've not really seen in calculus before. This is obvious for sums. Now, since there's some language that's going to show up in web work and in homework, I might as well take a few minutes to tell you some words. So what we will do on Friday is prove these rules and then do one of the crucial constructions that we're going to need moving on. And it's basically going to correspond to doing changes of coordinates. So what we're going to want to do is say, if you have a mapping, what happens with maps in differential forms? So that's going to be our task for Friday. But here is a little bit of vocabulary for you. Omega, a K-form is called exact if, some of you have seen this in differential equations, same terminology. If omega is d of somebody, for somebody in k who's a k minus 1 form. So where in Math 2700 did this show up? Did it really not?
Yeah.
So often they will talk about having an exact differential, which is in our language an exact 1 form. Michael, have you seen this in physics? Exact if, well, this is a 1 form, so it would need to be d of an eta where eta is in a 0, namely a function. So this omega is exact if it is d of some function.
So if p is the partial and q is the partial?
With respect to x and y. Yep. But this terminology works for higher forms as well. So we're going to talk about what this means in terms of physics by the end of next week.
So d of exact things is 0.
Ah. So omega in AK is called closed. Nothing to do with open and closed sets, nor open and closed doors. It's just called closed. If d of it is 0. And what did Ken just observe? If you have somebody who's exact,
d of it is closed.
d of it is
0.
0.
So the exact things are closed.
Right. Exact implies closed.
Is it
Ah.
not? Is it
Stay tuned for Friday. Question,
not?
converse. So let me just tempt you by saying, with Ken's question here, you now enter the world of topology. So this stuff is interesting not only because it's doing calculus, but also because, as you're going to see, it is actually starting to measure how sets in Rn look in terms of topology. I will explain that more over the next few weeks. Okay.